Welcome to another episode of the More Than Physics podcast, where, just like in the text publication, I talk about physics, mathematics, and science in general. But here, it's in the context of how my day-to-day in academia is going. Lectures, study routines, topics being covered, and things I learned or have been struggling to understand. A reminder that if you want to support the podcast or the publication, the Substack link is in the show notes. The first thing I want to say today is I love Feynman diagrams and quantum field theory in general. If you remember from last week, I was setting aside statistical field theory to study QFD for this week, and I just love it. I think it's my favorite course from the ones that I'm taking right now, which is some big thing to say, because I do love relativity, but quantum field theory has given me a new view of the world. I think I've understood some of the processes and some of the things that happen in a fundamental level in physics, and especially in particle physics, that I had no idea before. I'll keep my previous comments about the way that we deal with infinities being weird and indicating that there might be flaws in our current approaches, but over the past few days, I've really grown to thoroughly enjoy quantum field theory, the methods behind it, the reasoning behind it, and the things that we can achieve with it. To me, what's most surprising and most powerful about this whole thing is how quickly you can go from the Lagrangian to the behavior of the particles and the interactions. The Lagrangian is a function that will be familiar to most people that have done any kind of classical mechanics course, and it's a function or expression that describes how the energy of a system is distributed, how much of it is in the mass of the particles, how much of it is in the movement or momentum, and how much of it is in the interactions. Looking at this expression, which looks different for every field theory, you can already see immediately how the particles will interact. There's something called a coupling term in the Lagrangian usually that will tell you immediately, oh, yeah, this is how strongly these types of particles or this pair of particles interact. And that's where Feynman diagrams become very powerful, because just looking at the terms in the Lagrangian, you can see visually what the interactions will look like, because each interaction term, each of these coupling terms, will translate into a little drawing, into a vertex of a drawing. And so you can draw the lines representing the particles moving, and then whenever these lines meet, you can know exactly how they meet and then what that means mathematically. So basically, we developed along this semester many different methods for calculating things and representing things. But at the end of the day, it comes down to understanding how all of these mathematical things translate into silly little drawings. And in the day-to-day of a quantum field theorist or whatever person that works with quantum field theory, what you do is the other way around. You start with the drawings of the interactions, and then from the rules derived, you can understand what these drawings mean mathematically and calculate whatever you want. The energy of the interaction, how probable it is that it will happen, and so on. To me, that felt magical. And of course, it must be more complicated than that in the actual research environment when you're actually trying to understand things that nobody else has done before. But the methods themselves are really cool. All the way along this semester, there have been tricks and obscure little methods that at first didn't seem to be motivated by anything other than just trust the process. But at the end, everything clicked and everything makes sense together to get this logic of translating maths into drawings and drawings back into maths. To be honest, I don't really like this whole trust the process thing because it makes it difficult for me to actually take the steps and understand where we're going. For me, it's important to have this bigger picture, a vision of everything, to have the path laid out. But now that the course has concluded and I see what the purpose of each thing was, everything makes sense. And again, it's the course I'm enjoying the most out of the three I'm currently taking. Now, if I were to teach it in the future, when I eventually get to that point, I'd probably change the order of how we present things to try to keep students focused on the why we're doing this or that derivation, instead of losing ourselves in the maths and in the details as it currently tends to happen. I can safely say that the whole trust the process thing worked for me at least now at the end that I took a look at everything else that I've done in the semester and saw how things connected. But it wasn't ideal, and I do know that it can be a very high difficulty for people that study and learn in different ways. And I'd put some effort into trying to make it so that I wasn't relying on people being able to just go through the calculations without understanding what's going on. Right, so let me give you an overview now that my finals are coming up and I feel like I am prepared for it, of what this quantum field theory course was and what I think quantum field theory is about in general. So the need for QFD arises from the fact that when we describe quantum mechanics in the usual way, we're not taking into account special relativity. So the speed of light being constant, time dilation, and so on. And we need to take that into account if we want a more complete description of the universe. But if you just naively try to impose the conditions coming from special relativity into something like a quantum wave function, what you realize is that if you keep your number of particles consistent and fixed, then the description breaks. You break something called causality. I'm simplifying things a lot here, but essentially what's going to happen is that parts of your wave function are going to move faster than the speed of light. And you can't have that, can you? So eventually we found out that the way to keep quantum mechanics consistent with special relativity was to shift our description from particles to fields, because the number of particles can change, but the total energy and the total excitations of a field cannot change. That keeps constant. Essentially, on most cases, what you're going to have is that particles and fields will be interchangeable, because the fields will have just very localized peaks of energy, and these peaks of energy will be interpreted as particles. So essentially, you can come back and forth between the two representations. But in some cases, the field representation is very precise in describing processes that seem weird or janky in the particle representation, because what you're going to have is that these peaks of energy will split up sometimes and will fluctuate and will move in weird ways. That's why we hear about that duality, that particle-wave duality, about like an electron behaving sometimes like a particle and sometimes like a wave. Actually, it is always a wave. It is always an excitation of a field. But sometimes this wave is a lot more distributed and it just looks like a wave or behaves a lot more like what we would feel like a wave. And in some other times, this wave, this field is a lot more localized and the peak is a lot more pronounced. And then it behaves almost as if it were a localized particle, like we were used to thinking about the electron. So that justifies why we should have a field theory for quantum mechanics. And it turned out to be very precise and very useful. The two main things that we want to find out with this new quantum field theory is, what do these field excitations, essentially particles, do when they're alone? So how do they move when there's nothing around them? And how do they move when there are things around them? For example, other field excitations, maybe in the same field or maybe in different fields. So that's our object of study, and how we start studying them is through Lagrangians, as I mentioned before. In the case of a free field, meaning one that isn't affected by its environment and it's just free to propagate everywhere, the Lagrangian is very simple. It's composed of a mass term, if this field happens to have a mass, sometimes it doesn't, and a kinetic term coming from the movement of the field excitations. So now what we do is we take this simple Lagrangian as an example and develop with it methods to calculate some quantities that we might be interested in. One example is something called the partition function, which is just a fancy name for a distribution of states. So it tells us how likely a field excitation is to be in a certain state. And that depends on what kind of field you have. If you have a boson field, if you have a fermion field, I've talked about that in the previous weeks as well. And here is exactly where, to me at least, this course started feeling a bit pointless, like I mentioned at the beginning of the episode, because we were trying to calculate all these things and like develop methods to find some quantities. And I didn't realize why we were taking the steps we were taking. Like, we were making things way too complicated for what they needed to be. But that's just because we were using an example Lagrangian, something for a free field that didn't have any interaction terms. Because these methods all make sense when we're dealing with some more complicated Lagrangian with the coupling terms. in its expression. Because when you have that, then the fact that you can use the same methods that you develop for free fields now for interacting fields feels kind of magical. I've used that word a bunch of times today already, but it really does feel like that. I think it's just because of that bait and switch of showing all the methods, but on a simple Lagrangian, which doesn't feel like much, and then just applying the same methods for a very, very complicated system and seeing that not only it works, but it simplifies things a lot because we've done all of the groundwork, all of the mathematical groundwork with an easier system. And of course, historically, that's not exactly what happened. People tried to develop these cases as they needed them, right? These methods. But when we're teaching, the important thing is that people can see the methods and how they are made. And it doesn't make sense to use a complicated system for that right away because it would confuse people. I do get that. But for me, just seeing these methods before seeing interactions just felt a bit lost and without reason. But eventually we got to describing fields that are affected by other fields, and then everything clicked. And of course, the maths is a bit more complicated, and to understand it conceptually is also kind of complicated. But then Feynman diagrams, again, as I said, they help you so much because you develop them by understanding how the maths relates to drawings. And then when we're trying to do very, very complicated maths with systems that react in ways that we are not sure how yet, you can just look at the drawings and you have steps that you can use to draw these interactions, to draw these diagrams. And then from the diagrams, again, you can use something called the Feynman rules to figure out what each part of the diagram, each line, each vertex, each loop corresponds to in the maths. And that's basically what we did the whole course. That was the whole point. Deriving the methods that make our life easier when dealing with any kind of quantum field. As always, if you have any questions about quantum field theory or about anything else I'm learning and I'm talking about in this podcast, or if something seems unclear to you, feel free to ask me in the comments or in the chat or anywhere else. All the social links are in the description. On to the lectures. This week, they didn't have anything new, but they were in a way special because we had the last lecture for each of the courses. And for me, that always feels a bit melancholic. I'm simultaneously really happy to have concluded the course, assuming that I'm going to pass the exam next week, which I am optimistic about. So let's assume that. And that's a good thing, right? Happy to have concluded the course, happy to have taken that step, happy to have learned something. But at the same time, I feel like every time we finish a semester, we are essentially bidding farewell to something that just became comfortable to us. Because at the start of a semester, you're usually starting to see things that look mysterious to you, and you're coming in contact with an area of physics that you didn't have much experience in. And now you're just starting to feel like you're getting the hang of it, and you have to throw yourself into something new. These new things will hopefully have something to do with what you've just learned, or better yet, require you to use the knowledge to learn something else. But it doesn't cease to be a goodbye. It was a nice goodbye, though. General relativity even ended with snacks and sweets brought in by the lecturer. And so we all had a good time chatting to each other, asking and answering questions, and just remembering the cool things we learned this semester. It's a nice sense of community. And it reminded me that even though we're never going to stop learning, we can sometimes look back and see everything that we have learned, how much we already know about the universe, even we students. And it's one of those rare moments in which we can be proud of ourselves to be walking this complicated, difficult path that we chose for ourselves. I very often talk and write about how scary maths and physics look from the outside, and I usually argue that it's not that difficult to start learning, even for people that don't have experience and don't really know that much about maths and physics. I argue that it is a cool thing to learn, and it's less difficult than it seems. And that is true to an extent. I believe most people have the capability to engage with these quantitative topics in a deeper way than they think they can. And that can be very beneficial for most people. But I also have to recognize, and that's a challenge for me, and I assume for most physics students, that once you go this deep into a field, any field, it does get complicated, and you can look at yourself and be proud that you understand some complicated things and that you have some knowledge about the world that is not trivial and that you had to put in some effort to actually understand things. And especially in a field like this that requires hard work, effort, long hours, and some abstract understanding that is not intuitive, we should allow ourselves to look backwards sometimes and recognize how far we've come, rather than just looking forward all the time and constantly being scared of how much there is to learn and how much we still don't understand and how much we still need to travel to at least get to the level of the people doing research. Such is the curse of those who want to help science move forward. But I'm being dramatic. I promise I'll keep my philosophical ramblings about how this master's has been in general for next week, when my semester will officially be over. For now, I'll just keep preparing for the ever-approaching final exams while I still can. Regarding my study routine, there wasn't much variation between the weekdays, so I even have a hard time telling them apart. It was a consistent oscillation from reading material to attempting exercises alone to going through exams in a group setting, which always helps, like I said last week. And overall, the balance of all these different things has felt like constant learning was being achieved, which was very satisfying. It's not always like that. So I'm feeling prepared for the QFD exam on Monday. I don't think I'm going to ace it or anything. Of course, there's many parts that I still don't understand, and that's normal. But I do think I'm going to pass, and I am satisfied with what I've learned. But then, in the following few days, I'll have another refresher of statistical field theory before the final on Thursday. And finally, on Friday, I have my general relativity final, which I'll have to face with nothing more than a quick last look into the lecture notes and my experience working with black holes in my thesis, and vibes, I guess. I mean, clearly I'm not just going to wing it because you can't do that, but it's the course that I need the least grade in, and it's the final that is worth the least, and also the one I just feel more prepared and feel more experienced in. So I'll just have a quick review, and that should be enough. Next week, I'll let you know how that went, and probably also talk more general about how my first semester in the Masters was, what parts I liked, what parts I didn't like, and what the next steps are for me, academically, and for this podcast. If you want to be notified when that comes out, don't forget to follow the show on any of your favorite podcast platforms. Subscribe to the Substack publication, link in the show notes, to also receive all text posts, as well as to participate in the discussions and questions about the topics in the chat or in the comments sections. More Than Physics is a reader and listener supported publication, so thank you for being here and for sharing it around. I hope you enjoyed it, and until next time.